Alright, so we have the set A here, which is all points in R2 which satisfy this thing. So, first of all, let's just see what this looks like. So, I'll make this a little bigger. So this is x and this is y, and this is the line y equals x squared. Then A is everything which is inside this region. So it's going to be above the line y equals 0, but below y equals x squared. And it also, importantly, does not lie on any of these solid lines that I've drawn. So if you want to draw it more clearly, you could put like dotted lines along this line, along this curve y equals x squared. But anyways, A is this region inside here. So anyways, we want to show that every straight line through the origin contains an interval around the origin, which is in R2 but not in A. So any interval. So first of all, any line through the origin in R2, either you've got the line x equals 0, which is just a vertical line passing through the origin, but then any other line can be written as in the form x, as all points of the form xy, where y equals mx for some m, because the general equation of a non-vertical line is y equals mx plus b, and b tells you the y-intercept. We want the y-intercept to be 0, so that's passing through the origin, and so that's what we do. Y equals mx. So we'll start with x equals 0. Any interval through 0, 0. Along the line x equals 0 lies in a complement. And why is that? That's because in order to be in A, x needs to be greater than 0. And for all point on the line x equals 0, well, x equals 0, so it's not greater than 0. Okay, so that's good. So suppose L is a line consisting of points x, y, such that y equals mx. So this is the only other possibility of what such a line through a line through the origin could look like. It's either going to be x equals 0 or it's going to be y equals mx for some m. Okay, so if m is less than or equal to 0, then any interval through the origin along y equals mx lies in a complement. And that's because, well, if we look at this, if m is less than or equal to 0, then if you look at all some values on the interval will have x values less than or equal to 0, and those are automatically not in A. So we don't even need to worry about those. What we need to worry about is points on this line where x is strictly greater than 0. And if m is less than or equal to 0, then any number mx where x is greater than 0 will either be 0 or it will be a negative number. And here we require y to be a strictly positive number. So therefore, any point on the line y equals mx will be in the complement of A. Alright. So the tricky case is where y equals mx and m is strictly positive, because then this line will intersect the curve y equals x squared. So what do we do? If instead m is greater than 0, then if x is a number which is between 0 and m, then mx is going to be greater than x squared. Because m is greater than x, and you just... No, m is greater than x, and so you just take that inequality and multiply by x. And so the point x comma mx is not in A. Thus, any interval along y equals mx through the origin whose points x, y satisfy x is less than m will lie in a complement. And that's because, well, certainly we can do this because m is greater than 0, so we will be able to make an interval here. And so, like we said, so if you take an x which is less than or if you take this interval and consider a point on the interval where x is less than or equal to 0, it's automatically not in A. If you take a point on this interval and x is greater than 0, then, well, mx is going to be greater than x squared, so it's going to be an A complement. And so the entire interval will be an A complement. And that's what we wanted. Every straight line through the origin contains an interval about the origin which is in the complement of A. And that's what we've proven. We had to do different things depending on whether this was a vertical line or a line with negative slope or a line with positive slope, but this is what we had to do, and we did it. Okay, so next, so this is why are we considering this? What we're looking for is we want to find a function such that if you take the limit, we want to find a function from R2 to R such that you take the limit as a vector x goes to 0, 0 along any line through the origin. You take this limit as the point goes to 0, you'll get one particular value, but you can choose another path along which to approach the origin, and you'll get a different value. And if you do this, then so if we do this, then what that shows us is that this really emphasizes the fact that when you take a limit in multiple dimensions, in multiple coordinates, you really need, this limit needs to hold no matter how you approach the origin. Okay, so anyways, define f and h, blah, blah, blah. Show that each gh is continuous at 0. So, given h, let L be the set of all points of the form th, where t is in R. L is a line through the origin. By A, there is an interval I, which is a subset of L, such that the origin is contained in I, and I is also contained in the complement of A. And because of the definition of L, it's all vectors of the form th, this means that there exists some positive number t0 such that if t is less than t0, then th is going to be an I. And this is just straightforward from the definition of L. Okay? So then we can actually take the limit as t goes to 0 of gh of t. And this, by definition, is the limit as t goes to 0 of f of th. And so this is going to be the limit. If we're taking the limit as t goes to 0, then no matter what sequence of, or no matter how you approach 0, you're eventually going to lie entirely inside the interval I. So this limit is precisely the same as the limit as t approaches 0, where we only consider values of t such that the absolute value is less than t0. And then we have f of th. And now that we've restricted the t's that we're using in our limit definition, we're only using t's such that th is not in, no, such that th is in I. So th is in L. No, so th is in I, which means that th is in a complement. And so we're evaluating f at a point in a complement, and by definition that is 0. Rather, this would be the limit as t approaches 0, comma, norm of t is less than t0 of just the number 0, and then taking the limit of the number 0 gives you 0. Thus, gh is continuous at 0. However, if we let gamma equal, and now I have to change this because I sort of messed up when I did this. So it's going to be all points of the form x, then x squared over 2, where x is greater than or equal to 0. Then gamma is a subset of A. And why is that? Because for all x greater than... Oh, wait. It's going to be x is strictly greater than 0. Because for all x greater than 0, 0 is going to be less than x squared over 2, and that's obviously going to be less than x squared. Okay? So then, the limit as x approaches 0 along the curve, so I'm going to write x approaches 0 along gamma. And this makes sense because gamma is it's an infinite collection of points, and you can find a sequence of points in gamma here. So this should be x approaches the point 0, 0 along gamma. Okay. So, did I mess something? No. Okay, this is good. So as x approaches the origin along gamma of f of x, here x is a vector. And so this can be done because gamma is a collection of points. There's infinitely many. And so if you look at this formula and you take the limit as x, the real number, goes to 0, then you get points of the form x, comma, x squared plus 1, and these points will go to 0, 0. So we can, in fact, approach the origin along gamma. And we don't really have the language to say what I'm about to say, but what I'm really saying is that the origin is a limit point of gamma. And I guess what that means is that every neighborhood of gamma every neighborhood of the origin contains points in gamma. And that's true because you can take any rectangle and you can choose x small enough so that x will be within the x interval of the rectangle and x squared over 2 will be in the y interval of the rectangle. You would have to choose x less than, it'd have to be less than the rightmost edge of the x coordinate of the rectangle, and x squared over 2 would have to be less than the top coordinate of the top interval of the y coordinate, so you would need x squared over 2 less than y, so x squared is less than 2y, so you would need x to be less than the square root of 2 times y, where y is, of course, the upper limit of the y interval of the rectangle. But anyways, we can approach the origin along gamma. And we're approaching along a curve of points in A. So this is going to be the limit as x approaches 0 along gamma. Well, for any point on gamma, f of x is 1, because x is an A. So it's a limit of 1, which is just 1. Thus, f is not continuous at 0. And that's because we've taken the limit as x approaches the origin of f of x in multiple ways and obtained different answers. And so therefore the limit does not exist, and this continuity at the origin is equivalent to this limit existing, and the limit does not exist, so it's not continuous. And this is a really important exercise, particularly, I talk about this sort of with calculus students that I teach, because we talk about continuity in multiple dimensions. So this is like a Calc 2 thing. We'll talk about continuity in multiple dimensions, and we'll say, okay, so sometimes you can check that a limit exists by doing some algebraic manipulation. Or you can verify that a limit does not exist by approaching the origin along, say, 2 different lines, and proving that you get different values when you approach along those different lines. However, just because you approach this, I mean that this might be something that's a little bit obvious for someone at the level of Spivak, but I don't know, it's nice to mention it again. So just because you approach the origin along every single line and get the same answer does not mean that the limit exists. You have to consider any possible path along which you can approach the origin. And so if you want to prove that a limit exists, typically like in Calc 2, you need to do some sort of algebraic manipulation and cancellation in order to get the limit. And through analysis and stuff, we'll come up with other estimates and stuff that you can use, like if you go on to do more analysis type stuff. But yeah, so this is a really good exercise because it shows you that you can get the same limit as you approach the origin along any line that you choose, but the limit still does not exist. And yeah, that completes the exercise, and we are done.